distinct groups of a given order. We start by stating a property of discrete groups, that finite groups with prime order are cyclic. And this can be shown as follows. Consider a group of order G, where G is a prime number. So that means the only divisors of G are 1 and G itself. Now we already know from Lagrange's theorem that the order of any element of G should be a divisor of the order of the group. And therefore the order of any element of this group G should be a divisor of G. And we already know, because G is prime, that the divisors of G are 1 and G only. So that means if G is prime, then the order of the elements of the group should either be 1 or G. Now, which is the element that has order 1? So the order of an element is defined as the smallest number n such that a to the power n is equal to the identity. Then we will say that the order of the element A is n. So if the order of an element is 1, that means a to the power 1 is equal to E. But a to the power 1 is simply A. Or in other words, A is equal to E. So the element of order 1 in a group is simply the identity element. And there is only one identity element in a group. It is unique. And therefore, if we have a group of prime order, one of the elements could be the identity, which is of order 1, but the other elements, the elements other than the identity, should be of order G only, because that is the only other order that is allowed for elements of a group of order prime. So then the elements can be written in the following way. G will be first of all E, and the other elements all should be of order G. So they can be written as A, then A square, A cube, and so on up to A to the power G minus 1. So if we take A to the power G, this will be E because A is of order G. And we can also see that not only A square, A cube, etc. will all be of order G as well. So the group is given by G equal to A to the power n, where n is equal to 1, 2, 3, etc. up to G. So all the elements are generated by a single element A and is therefore a cyclic group. So that proves our statement that a group of prime order is cyclic. And obviously, since it's a cyclic group, it is abelian as well. So now we first consider the number of distinct groups of order 1. So G is equal to 1, and therefore the group contains only one element, and that should be the identity element. So the group of order 1 is simply the group containing a single element, which is the identity. Now group of order 2. From Lagrange's theorem, we know that the order of the element should be either 1 or 2 because they are the divisors of the order of the group. So element of order 1 is E, and we can have one more element, and that element should have order 2. So we write it as A. Now the element generated by taking powers of A are A square and so on, but A square is equal to E because it is of order 2. So the group can be written as G is equal to A comma A square, which is the identity. Obviously, this is generated by A and it is of order 2. So it is the cyclic group of order 2, and we denote it by Z2. In general, a cyclic group of order n is denoted by Zn. So we now consider group of order 3. 3 is a prime number, and we already have proven the statement that a group of prime order is a cyclic group of the same order. So G should be the cyclic group Z3 of order 3. Now we consider groups of order 4. From the Lagrange's theorem, the order of the element should be the divisors of the order of the group, and the divisors of 4 are 1, 2 and 4 itself. So we will consider different possibilities of constructing a group with 4 elements. Obviously, the element should have order 1 or 2 or 4. So let us consider the first case where we take the element to be of order, one of the element to be of order 4. So that will generate 4 elements. Say if we call this element by A, the elements generated by that element will be A square, A cube and A to the power 4, which will be equal to E because A is of order 4. So this has generated 4 elements, and therefore it is a group of order 4. Obviously, this is a cyclic group of order 4. So the first possibility for a group of order 4 is that it is a cyclic group of order 4. And for the second possibility, we will assume that there is no element with group of order 4, because if it is so, then the group will be the cyclic group. Okay, so we have already done that, and we will now assume that the element is of order 2 and call it as A. Then that means the elements generated by it are A and A square, but since it is of order 2, A square is equal to E. So we now have 2 elements, A and A square equal to E. The group should be of order 4, so we need 2 more elements. The third element cannot be an element of order 4, because then it will generate 3 more elements. The fourth element will be the identity, but that is already be taken care of by A square. But we cannot have 3 more elements, we only need 2. So the third element should also be of order 2. So we have the third element, which we denote by B, but then B square is equal to E. So that is already there. So we have 1, 2, 3 elements. We need the fourth element. That cannot be of order 4. So that should be also of order 2. So we call it C. So the elements generated by these 3 second order elements are A, B, C, and A square equal to E. B square is also equal to E, and C square is also equal to E. So we have 4 elements, A, B, C, and the identity. So that is the other possibility for a group of order 4. But that is not all. It should satisfy this set of elements with these properties that we just stated, that A square equal to E equal to B square equal to C square should also satisfy all the properties that are required for a group. So this can be checked easily in these cases of elements with groups with fewer orders, like 4, 5, 6, etc., with the help of the multiplication table, writing out the multiplication table explicitly. For that, we first construct the multiplication table. Obviously, the multiplication table will have say G rows and G columns. In this case, G is 4, and therefore it will have 4 columns and 4 rows. And the labels of rows and columns are given by the elements themselves. So we consider the multiplication table for this particular choice of elements. And we will check whether it is possible to construct a consistent multiplication table. what we mean by a consistent multiplication table will be clear soon. So the row labels are the elements of the group E, A, B. Sorry, the column labels are the elements of the group E, A, B, and C. The row labels are also E, A, B, and C. Now, some of these cells of the multiplication table can be easily filled. So look at the first column. For example, this cell is obtained by the product of E with E, but that is simply E. Again, this cell is obtained by A times E, which is A. So the first column is obtained by multiplying the elements of a group or the corresponding row labels with E, and therefore they will be simply those row labels only. So we can simply repeat these row labels in the first column corresponding to the identity element. The same thing happens for the first row that correspond to the identity element, because the elements there correspond to the multiplication of the corresponding column labels with the identity element, and therefore they are simply the column label. So I can repeat this over here and repeat that over there. Further, we also have this property that A square is equal to E, and therefore this cell, which is actually this A times this A, which is A square, is E. Again, this cell is B times B, that is also E. And this cell is C times C, that is E. Okay, so the only cells that needs to be determined in this multiplication table are cells labeled 1, 2, 3, 4, 5, and 6. Okay, so we can actually use the rearrangement lemma uh, to find out the possible values of these cells. So the rearrangement lemma says that any row, or in fact each row and each column of the group multiplication table should contain each element of the group once and only once. Okay, so that means if we consider the row corresponding to the element A, we have two vacancies here, cells labeled 1 and 2, but that row already contains the elements E and E. The group contains two more elements, B and C. So the possible choices for these cells 1 and 2 are B or C. But then if you look at the column already contains B. So cell 1 cannot be equal to B. So the only remaining possibility is that this is equal to C. Okay, now what about the possible choices for 2? Already in the row we have A and E. Okay, and here we have C also. The only remaining possibility is B here. Now we look at this column corresponding to the label C. So that column contains C, B, and E. The only remaining element is A. So cell number 4 should contain A. Now we look at this row corresponding to B. The row already contains B, A, and E. The only remaining possibility is C, and therefore cell 3 should be C. Now look at the cell corresponding to A. A, E, and C are there. The remaining possibility is B, and therefore cell 5 should be B. Now looking at the row corresponding to C, we have say already C, B, and E there, and therefore this should be equal to A. Now we can see that each row contains every element of the group, and each element is contained only once in that row, and the same for the column. So rearrangement theorem is satisfied. So this is what we mean by a consistent multiplication table. So this choice of a group with 3 elements of order 2, and obviously the identity element is also a possible group. Okay, so now we have constructed, we have identified 2 choices for groups of order 4. The first one is obviously the cyclic group of order 4, and the second one is group with elements A, B, C with A square equal to E equal to B square and C square also equal to E. Now, looking at the group multiplication table, we have the following property. So, B times A is equal to C, and A times B is also equal to C. So that means AB is equal to BA, and then for each pair of elements you could see that say the element say G1 times G2 is equal to G2 times G1, simply looking at this multiplication table, and therefore the group is abelian. So the second group that we constructed over here is in fact an abelian group, but it is not a cyclic group. Okay, so these two groups are said to be, they are in fact non-isomorphic because the group multiplication table for this first choice and the second choice are different. We next move on to distinct groups of order 5. So G is equal to 5, which is a prime number, and we already know that if the group is of prime order, then the group should be a cyclic group. Okay, so the only possible group over here is Z5, which is cyclic group of order 5. So next, distinct groups of order 6. So we first note that the divisors of G equal to 6 are 1, 2, 3 and 6, and therefore the elements of the group should have orders one of these numbers only. So 1, 2, 3, 6. So we will first start with a possible choice with the group generated by an element of order 6. So call it A. The group elements would be A square, A cube, A4, A5, A6, which would be equal to identity. So that's a cyclic group of order 6. Now for the second choice, obviously the group element, none of the group elements could be of order 6. So the next choice is 3. So we will assume that there is an element A which is of order 3. It will generate 3 elements, A square and A cube, but that is equal to E because the order of the element A is 3. Now the group is of order 6, and therefore we need 3 more elements. Okay, so assume that the fourth element other than A square and identity, let us call it say B, and let us assume that it is of order 3, and we will check whether this possibility works out. If it is of order 3, it will generate 2 new elements, B and B square. Obviously it will form B cube also, but B cube is E, which is already given by A cube. So only 2 new elements are generated by this second order 3 element B. Now how many elements do we have now? A square, then A cube equal to E, and B square. We have 5 of them. The group should be of order 6, so we need one more element. So that can be of order 2. So we call that element by the name C. Then it generates C and C square, which is equal to identity. Okay, so it adds a new distinct element. So the second choice for a group of order 6 can be taken to be an element A which is of order 3 and element B which is again of order 3. Together they generate elements A square, A cube is E, so is B cube, and then B and B square, and a third element C uh, which is of order 2, so that C square is also equal to E. So now we need to check whether it forms a consistent group multiplication table. So we will construct our group multiplication table. It will have 6 rows and 6 columns corresponding to 6 elements of the group. The column labels will be given by say E, A square, B square and C. But we will choose the row labels in such a way that the diagonal elements of the group multiplication table are all filled with the identity element. Okay, and how can we do that? First we note that the first column corresponds to E and the row should be such that if I multiply that label with E, I should get the identity element. But then E times E is identity. So the first row should be labeled by E. Now look at cell 2, 2. The column label is A and the row label should be another element such that when we multiply that element with A, we should get E. But we already know that A cube is equal to E. And therefore, if we choose this label to be A square, this cell will be A square times A, which is A cube, and therefore equal to E. Similarly, we consider this cell where the column label is A square and the row label should be the inverse of A square. So that when we multiply A square with that element, we will get E. So inverse of A square is A because A cube is E. This is what happens for all other rows as well. Okay. So the inverse of A here is A square. The inverse of A square here is A, and the inverse of B here is B square, and so on. And if we arrange the row labels in such a way that each row corresponds to the inverse element of the label of the corresponding column, then we will have the diagonal elements equal to the identity of the group. So having arranged these labels, then we can fill up some of the cells of the multiplication table. As we have already seen, the row corresponding to the identity element can be easily filled up. And similarly, we can fill up the column corresponding to the identity element. That column will simply be a repetition of the row labels, and the row corresponding to the identity element will simply be the repetition of the column labels. Further, the way in which we have arranged the multiplication table is such that all the diagonal entries are also fixed, that is equal to E. We can fill up some more cells. So if we look at this particular cell, the column label is A square and the row label is also A square, which is A square times A square, which is A to the power 4, which I can write as A cube times A. But A cube is simply identity. Now identity times A is A, and therefore this cell is A. So that cell is fixed. So the next thing is this cell, which is actually A times A and which is A square. And the same happens over here in this cell, which is actually B square multiplied by B square, which is B to the power 4. But then B to the power 4 is B cube times B. But then B cube is E, as we have chosen B to be an element of order 3. And this cell is simply B times B, which is B square. Okay, so we have now 16 cells that needs to be determined and checked whether it will lead to a consistent group multiplication table. Now we consider cells labeled 1 and 2. Okay. Now, rearrangement lemma says that this row should contain every element of the group once and only once. And in fact, these columns corresponding to B and B square should also have the same property. Okay. So, for consider cell 1. Okay. So, the possibilities are, so this row already contains A square and E. So the remaining possibilities are B, B square and C. So one can have those possibilities. But look at the column here. The corresponding column already contains B and B square. So the only possibility for one is actually C. So this should be C. Now look at cell number 2. Already seen, the row contains A square and E, and the column contains B and B square. Again, the only possibility is C. But then the rearrangement lemma says that it is so every row should contain an element once and only once. But here C will be repeated, which cannot be allowed. So that means this choice of elements with these properties cannot form a group of order 6. So we have to avoid, we have to discard this possibility. So far we have only constructed one group of order 6, which is the cyclic group of order 6. And the second choice that we tried does not work. So what does that mean? I cannot have an element of order 3 in my group of order 6. So, and also we have already considered a group generated by a group of order 6. So we will now assume that the element of the group that we are going to consider is of order 2. The elements that A generates are A and A square, which will be equal to E. Sorry about what I said earlier. What we have just shown here is that the second element B cannot be of order 3. And not that the first, no element can be of order 3. Obviously, A can be of order 3. Okay. So, A is of order 3. That means it will generate elements A square and A cube, which will be equal to E. Okay, the second element B cannot be of order 3. That is what we have just shown. So it can be of order 2. So if it is of order 2, it generates B and B square, but B square is already E. So now we have elements A square, E and B, 4 of them. We need 2 more elements. Okay, so the remaining 2 elements can be chosen to be of order 2. We name them C and D. C generates C and C square. C square is already E. And D generates D and D square, which is also E. So we now have 6 elements: A square, E, B, C and D. So as a second choice of a group of order 6, we may consider this set of elements: A square, C, B and D, with A cube equal to E, B square equal to E, C square equal to D square equal to E. The next thing to be done is to check whether it is possible to have a consistent multiplication table for this. That means whether this set of elements satisfy all rules required for a group. As we have done earlier, we again start with constructing the multiplication table. We label the rows and columns in such a way that the diagonal entries are all identity elements. So that means the label for row corresponding to a given column should be given by an element that is the inverse of the corresponding column label. So that means for this cell, the row label is, the column label is A, the row label is chosen to be its inverse, which is A square, and so on. Then the first row, the row corresponding to the identity element and the column corresponding to the identity elements are filled up in the way that we just discussed, and it is quite easy. And the diagonal entries are all identity elements. And we can also fill up these cells. So this corresponds to column entry A square and row label A square, and therefore the cell should have value equal to A square times A square, which is A to the power 4, which is A cube times A. A cube is E, and therefore this element should be E times A, which is A. Similarly, this cell is obtained by taking the product of A with A, but that is A square. And we have the remaining 18 cells to be identified and checked for consistency. Okay, we will now first consider the cells 1, 2 and 3. So let us concentrate on cell number 1. The rearrangement theorem says that the rows and columns, every row should contain each element of the group once and only once, and every column should contain every element of the group once and only once. So now the row corresponding to the cell number 1 contains elements A square and E, and the column contains B and E. So the only remaining possibilities out of the remaining elements are C or D. So we have a choice. We can either take C or D. We will start with the choice. This cell is equal to D. So now we look at cell number 2. We already have A square D taken care of in that row, and the column contains C. So the only remaining element of the group is B. So cell number 2 should be B. Now look at the column. It contains identity A square, D, B. So the only element remaining is C, and therefore cell number 3 should be filled with that. Okay. The next thing that we notice is the cell number 1 is actually D, but that is A square times B. So which means that A square times B is equal to D. But D is an element of order 2. So that means if I take the square of this, A square B square, this should be equal to D square. But D square is equal to identity. So what does that mean? A square B inverse is equal to A square B itself. That's why A square B times A square B is identity. But we already know that the inverse of the product is the product of the inverses taken in the reverse order. So this inverse is simply B inverse times A square inverse. On the right hand side, we have that equal to A square B. But what is B inverse? Since B square equal to E, B inverse is B. So this means B times, what is A square inverse? A square inverse is A, because A cube is equal to E. So the left hand side is BA and the right hand side is A square B. But that is A square B is simply equal to D, as we have chosen here. So that means BA is equal to D. Now look at this cell in the multiplication table, cell number 7, which has a row label B and column label A. So this cell is B times A, that is equal to D. So this should be equal to D. Now we can proceed in a similar fashion with cell number 2, which says that a square c is equal to b, and we can do a similar calculation and show that ca is equal to b, and I have explained that here in this notes. So this will be b, and we can start with cell number c, which says that a square d is equal to c, which can be which will lead to the result that dA is equal to C. Therefore, this will be equal to C. So that is what is shown in this figure. And next, we look at cell number 4. Okay, so this row already contains A square and E, and the column contains B and D. So the only remaining possibility is C. Now, we look at cell number 5. It contains A square, E and C, and column contains C and B. So the remaining possibility is only D. And as we can see, simply looking at this row, we can see that cell 6 should be equal to B. So there is no possibility. So now we can start with cell number 4, which says that A times B is equal to C. And then we can see that C is of order 2. So C square should be identity. That means AB square should be identity. And we can proceed exactly the same fashion as we did with the values in these cells and show that BA square is equal to C. So that means this cell should be equal to C. And we can start with cell numbers 5 and 6, follow the same procedure and show that this is equal to D and this is equal to D. So now we look at cell numbers 9 and 10. So already we have B, D, C and E here, and C, B and D here. So the possibilities for cell number 9 and 10 are in fact A and A square. Could be A and A square. So we need to determine precisely what they are. For that, we note the following. See, this cell number 9 is equal to B times C. Okay, so cell number 9 is equal to B times C. But we look at cells 6 and 15. So they are cells 6 and cell number 15. Okay, so cell number 9, sorry, we go back to the other figure. Cell number 9 is equal to B times C. Okay, cell number 9 is B times C. But now we look at cell number 6 and 15. Okay, so what does cell number 6 say? It says that A times D is equal to B. So B is equal to A times D. And cell number 15 says that D times A is equal to C. So C is equal to D times A. So which implies that B times C is equal to, B can be replaced by AD and C by DA. And because of the associativity, I can take this product first, which is D square. So A, D square A, but D square is nothing but the identity. Over here, we have chosen D square to be equal to E because it's of order 2. So this is E. So E times A is A and A times A is A square. So the result is BC is equal to A square. But cell number 9 is nothing but BC. So this should be equal to A square. Now examining this row, cell number 10 should be filled with the only remaining element, and that is A. Okay. So as we can see, if we look at this column corresponding to D, there is only one vacant cell. It is filled with D, C, B, A and E. So the only remaining element is A square here. Now we can look at this row. So in that row, we have elements C, B, D and A square, and therefore column number 13 should be, cell number 13 should be filled with element A. Now look at this column. A, B, D, C appear here. So only element that is not appearing in this column is A square, and therefore there should be A square. And similarly, looking at this row, we can see that this should be equal to A. So we have been able to, fill up the cells in the multiplication table in a consistent manner. Okay, so therefore, this choice of elements having these set properties form a group of order 6. So we have already identified two possibilities for groups of order 6. The first one is a cyclic group of order 6, and the second one is something like this, okay, with the group multiplication table given by this. By examining the group multiplication table carefully, we can see that this is not an abelian group. We should now look for other possibilities of constructing group of order 6. So the possibilities that we considered were the group generated by an element of order 6 which resulted in Z6, and the second possibility was that one of the elements was of order 3 and the remaining elements B, C and D were of order 2. So 2, 2 and 2. So we should consider the other possibility that we will construct a group of order 6 with elements consisting of order 1, which is the identity, and the remaining elements being of order 2. So we need 5 such elements. Okay, so it will be E, then A, B, C, D. No, I can't have. So F. So before checking whether it is possible to construct a group of order 6 with this choice of elements, we will first state a property of the groups formed completely by the elements of order 2 except for the identity. Okay, the statement is the following: a group in which each element except identity is of order 2 is an abelian group. So we can prove this in the following way. Suppose we have a group G and every element in the group except identity is of order 2. So if A is not equal to the identity element, then A square should be equal to E. Let A and B be such two elements of order 2. So that means A square equal to E and B square equal to E. So A square equal to E means A inverse is A, and B square equal to E means B inverse is B. Now consider the product of the elements A and B. Remember, A is not the identity and neither is B, and therefore their product cannot be A or B. It should be another element. So it should be an element of order 2, because all elements in this group are of order 2 except for the identity. Okay, so the product AB can be identity only if A is identity and B is also identity. So we have taken A and B not to be identity. So in that case, this will result in this product will be an element of G other than the identity, and therefore is of order 2. So that means AB square is equal to identity. So AB square equal to identity means AB is inverse of itself. So AB inverse is equal to AB. But AB inverse is simply B inverse A inverse. So that means B inverse A inverse is equal to AB. But since A and B are of order 2, B inverse is B and A inverse is A. So this is A, sorry, this is B and this is A. So which implies that BA is equal to AB. Or in other words, the order of multiplication doesn't matter here. And this is true for any element in that group. That means group G is abelian. So the property is that if all elements in a group other than identity is of order 2, then that group should be an abelian group. Okay, so we now come back to our proposed choice of elements for a group of order 6, where we take 5 elements A, B, C, D and F to be of order 2 and one element, the identity element, to be of order 1. So now, because of this property that we just proved, the elements, sorry, this group should be an abelian group. So they should commute among themselves. That is, for any two element A and B, so AB should be equal to BA. Okay, so we now consider an element A, so two elements A and B other than the identity. Okay, so A is not identity, B is not identity. So this will definitely mean that A times B should be one of the possible choices C, D and F. Okay, so C, D and F are all of order 2. So that means AB square is equal to identity, because C, D and F are all of order 2. So its square should be equal to identity. So then we can do the following. We can construct a set of elements starting with the element A, then B, then A times B. Okay. Now A square equal to E, B square equal to E, AB is equal to AB, and AB square is also equal to E. So we see that, under group multiplication, these elements form a closed set. And all other properties like associativity, etc. follows from the group property itself. So that means the elements A, B, AB and E forms a subgroup of the group G. And what is the order of this subgroup? It has 4 elements, and therefore the order of this subgroup is equal to 4. So if we take this choice for forming a group of order 6, then we will be able to construct a subgroup of order 4, this group. But then Lagrange's theorem tells us that it is, any subgroup of a given group should be such that the order of the subgroup should be a divisor of the order of the group. Now, order of the group here is 6, and order of the subgroup constructed this way is 4, and 4 is not a divisor of 6. Therefore, the only possible resolution of this contradiction is that we cannot choose, or we cannot construct a group of order 6 with this choice of elements. Okay, so now we have already exhausted all possibilities, and therefore we identify that for a group of order 6, we only have two distinct possibilities, two non-isomorphic possibilities. The first one is a group generated by an element of order 6, which is a cyclic group of order 6. And the second possibility is the one given here, where we have an element of order 3 and 3 elements of order 2. And this group, as we have seen from the multiplication table, is obviously non-cyclic, non-abelian as well. We will now consider the properties of a set of generators of a group. Remember, the set of generators of a group are a subset of the elements of the group such that by taking the powers and the products of those elements themselves, we can generate all elements of the group. And this should be a minimal subset of the group G. Okay, so the property is the following. A subset S of elements of a group G is a system of generators of G if and only if there exists no proper subgroup of G that contains S. A proper subgroup of G means a subgroup such that G contains at least one element that is not in the subgroup. Okay. So we will prove this in two steps. First, we prove that if we have a set of generators, then there exists no proper subgroup of G that contains S. And in the second step, we assume that there exists no proper subgroup of G that contains S. Then we will show that this implies that the set of elements S is a set of generators of the group. Okay, so let us consider the first one. Let S be a set of generators of G, and assume that there exists a subgroup H of G such that this set of elements is contained in that subgroup. Okay, so S is a group of elements which generates the group. Okay, and there exists a subgroup of H. H is a subgroup of the group G, and these elements are contained in the subgroup. So it is a subset. And what we need to show is that there exists no proper subgroup H that satisfies this. Okay. It still allows for the possibility that H could be equal to G, the group itself, but H cannot be a proper subgroup of G if it contains the set of generators. Okay. To see this, we first consider the statement that S is a subset of H. So that means every element of S is an element of H also. Okay. So now if I take the powers of elements of S, they will be elements of H itself. That is because every element of S is an element of H, and if I take power of element of H, it should be an element of H itself because H is a group. And closure property demands that the product or the powers of any element of that group should be an element of the group itself. Okay, so if I take the products of elements of S or the powers of elements of S, all of them will be elements of H also because of the closure property, and since H is a subgroup. So that means all elements generated by them, all elements generated by S should be elements of H as well. Okay, so the elements generated by S are elements of H, but then we have also stated that S is a set of generators of G, and therefore the set of elements generated by S is simply the group G. But as we have seen here, the set of elements generated by S should be a subset of H as well. So that means G should be a subset of H. Okay, but we have already said that H is a subgroup of G. Okay, so these two statements, that G is a subset of H and H is a subgroup of G, can be true only if H is equal to G. So if we start with the assumptions that S is a set of generators of G and that there exists a subgroup of G which contains this set of generators, then it immediately says that H should be equal to G. Okay, so that means H cannot be a proper subgroup of G. It should be G itself. So the first part of this property has been proved, which says that if S is a set of generators of G, then there is no proper subgroup of G that contains S. Okay. Now to the second property, which is that if we assume that there exists a set of elements of G that is not contained in any of the proper subgroups of G, then they will be a set of generators of G. Now assume that there exists no proper subgroup of G that contains a subset S of G. There is some subset S of G, but there exists no proper subgroup of G that contains it. Now we consider the set of elements generated by this subset S. Okay, so we have a subset of G and we have some elements in that subset. We consider the powers of the elements of S and the products among themselves. Obviously, they will form a group because it will form a closed set. Okay, so the elements generated by S forms a group. Now S is a subset of elements, subset of G, and therefore all elements of S are elements of G itself. Okay, so elements of elements of S are elements of G, and therefore the elements obtained by taking the powers of elements of S and by taking the products of elements of S among themselves are also elements of G, and therefore the set of elements generated by S are elements of is a subset of group G. Okay, so 2 points. First, the set of elements generated by S forms a group because they form a closed set, and the elements in that group are elements of the group G because they are formed by taking the powers and products of the elements of S, which are elements of G also, and therefore the group generated by S is a subgroup of G. Okay, so the important result is the group generated by S is a subgroup of G. But then we also assume that there exists no proper subgroup of G that contains a subset S of G. Okay, so obviously the group generated by S contains S, and the group generated by S is a subgroup of G, but it cannot be a proper subgroup because of this assumption that we made. The only remaining possibility is that the group generated by S is in fact the group G itself. So which proves that If there exists no proper subgroup of G that contains a subset S of G, then the subset S generates the group. Therefore, it forms a system of generators.